When data volume scales to millions of requests per second, engineers face a strict physical tension. You are trying to take a massive, chaotic surge of incoming information and force its way through rigid, finite computational bottlenecks. If you route that flood into a traditional, vertically scaled architecture, the math breaks down almost immediately. A single server node can only parse data at the speed of its CPU clock cycle. When incoming network request volume exceeds that processing speed, memory buffers hit their capacity limits. For the system we are examining today, the target metrics are severe. It must successfully ingest and process over 100,000 independent events per second, and it must maintain a total round-trip latency budget of under 50 milliseconds. If you direct that specific load against a standard REST API tied to a monolithic database, you hit predictable failure states. Connection threads become completely exhausted. The system begins dropping network packets at the interface card, and the state of the client applications permanently desynchronizes from the server. Surviving this load is a problem that cannot be solved by purchasing faster hardware. It requires abandoning vertical scaling entirely in favor of an architecture built on extreme decoupling and asynchronous routing. This diagram shows the macro-level architecture designed to solve that problem. It is a distributed network composed of numerous interconnected subsystems, each handling a highly specific portion of the processing load. The physical boundaries of this journey are defined by 2 points: the entry gateway cluster on the left, where external traffic first makes contact, and the primary database cluster on the right, where the final state is committed to disk. To understand exactly how this system maintains its target metrics under load, we must isolate a single discrete data token and trace its critical path, step by step, through these execution layers. The efficiency of this architecture relies on a specific set of rules. The system succeeds based entirely on how state transitions are handed off between these isolated components. Our data token begins its journey at the system perimeter, making contact via a high-throughput gRPC protocol. This maintains a persistent, multiplexed connection, avoiding the overhead of constantly opening and closing TCP handshakes. The load balancer uses a stateless round-robin algorithm, distributing thousands of requests across gateway nodes without deep packet inspection. Inside, the perimeter validation layer drops malformed packets instantly. Our token passes and is serialized into a highly compressed binary format to minimize network transit weight. At this exact moment, the system experiences a massive, unpredictable spike in global traffic. The ingress layer is suddenly accepting more serialized tokens per second than the internal nodes can theoretically process. To prevent memory exhaustion, the system triggers a backpressure mechanism. Downstream components signal the edge gateways to temporarily buffer incoming requests or dynamically limit the connection rate, slowing the intake valve before internal buffers overflow. By completely isolating connection pooling and validation at this outer edge, the architecture guarantees that sudden traffic surges cannot cause cascade failures deeper inside the primary processing nodes. At the message broker cluster, the broker reads the token's routing key, running a hashing function to slot it sequentially into an exact partition. It writes to an immutable log. An offset index counter advances, definitively recording it safely stored, even without available compute nodes. Instead of the broker forcing data downstream, internal compute nodes operate in consumer groups. Instead of forcing data downstream, compute nodes operate in consumer groups. They independently pull tokens from broker partitions at their maximum processing speed. This asynchronous handoff is the most critical boundary in the architecture. Decoupling ingestion from computation is the exact mechanism that prevents slow, heavy database writes from blocking fast, lightweight user inputs. A stateless compute node eventually pulls the broker, claiming our token and pulling it from the partition for actual processing. This chart compares the latency of memory architectures. To maintain the system's velocity, this compute node holds and processes our token entirely in RAM, executing operations in microseconds rather than incurring the heavy millisecond penalty of traditional disk I/O operations. Inside the node, the system reads raw data, combining it with cached metadata from an in-memory store to form a rich data structure. Simultaneously, the node manages thousands of tokens using a non-blocking, event-driven threading model across parallel threads without locking shared memory resources. But we must account for failure. If this specific hardware experiences a catastrophic power loss while actively holding our token in RAM, the token vanishes. Because the compute node never sent an acknowledgement back to the message broker, the broker's timeout window eventually expires. The broker simply makes the token available again, allowing a healthy secondary compute node to pull it and retry the exact same operation. Our second compute node successfully completes the transformation and dispatches the enriched token toward the final storage layer. The compute core achieves its extreme velocity precisely because it stores no local state. The nodes are designed to be completely disposable, allowing the system to scale them up or kill them off dynamically in response to load. The token arrives at the primary storage node. Relying on eventual consistency, the database instantly signals a successful write upon entering memory, before securing on disk. Meanwhile, a consensus protocol propagates the state to replicas, achieving permanent durability only when a mathematical quorum confirms receipt. If a network partition causes two separate compute nodes to modify the exact same user record simultaneously, the database relies on version vectors, rejecting the older timestamp and applying the most recent state. The architecture of this database layer enforces a strict mathematical reality. The engineers intentionally sacrificed absolute real-time data consistency to guarantee that the system remains available and tolerant to network partitions under extreme load. This diagram shows the unbroken path our token traveled from the ingress gateway through the distributed broker and compute node into final storage. A final acknowledgement signal then fires backward, confirming the transaction. This 42-millisecond journey was mostly consumed by physical network transmission limits, with actual system computation requiring less than 5 milliseconds. Because of this specific design, the system effortlessly sustains a massive throughput of 100,000 events per second, a volume that would crash a tightly coupled monolithic database in a matter of seconds. Isolating the validation, queuing, compute, and storage layers ensured that a spike in one specific area, like a surge in incoming connections, could not consume the CPU cycles required to execute database writes. The defining lesson of the data trace is that you do not achieve extreme system scale by attempting to eliminate latency. You achieve it by hiding latency inside asynchronous pipelines. The most critical design choice in this entire circuit is relying on an immutable message log as the absolute source of truth, rather than the primary database. This approach represents a new philosophy for system engineers. Instead of trying to build components that never fail, you design an architecture where localized hardware failure is the assumed default state, and the system seamlessly routes around it. The cost of this decoupling is a massive increase in operational complexity. Without robust distributed tracing and observability tools, debugging an error across dozens of stateless, asynchronous nodes becomes mathematically impossible. The ultimate achievement of this architecture is an illusion. It successfully orchestrates thousands of highly distributed, chaotic, and disposable components to behave, from the user's perspective, exactly like a single, unbreakable machine.